Sound transmission. Sound transmission refers to the propagation of sound waves from one space to another through building elements, for example, such as walls, floors, ceilings, doors, and windows. It occurs when sound energy is transmitted through the physical structure of a building, allowing it to be heard in adjacent rooms or areas. Mode of transmission. Airborne transmission. Structure-borne transmission. Airborne sound transmission. Airborne sound is the most common type of sound transmission and occurs when sound waves travel through the air from a sound source to a receiver. Airborne noises are transmitted by air in atmosphere such as the radio, the barking of dogs, or people carrying on conversations. When sound waves traveling through the air reach a building element, they hit it and cause it to vibrate. These vibrations travel through the structure or building and are radiated out the other side. It can pass through openings, gaps, or penetrations in building elements. Sound can also pass under doorways, through ventilation, over, under, around, and through obstructions. This is as opposed to structure-borne sound that results from an impact on or a continuous vibration against a part of a building fabric, resulting in sound being radiated from an adjacent vibrating surface. Causes of airborne noise. These noises are caused by vibrations which transmit through a medium and reach the ear or some other form of detecting device. Sound is measured in loudness, decibels, decibel, and frequency, hertz, hertz. It is ultimately the sound which can only be transmitted only through air and can be perceived at least by homonia and hence have frequencies ranging in between 20 Hz to 20,000 Hz. Poor detailing or poor standards of workmanship can result in airborne sound transmitting directly between spaces, for example through gaps around the edge of doors, and may result in flanking sound, where sound travels around a separating element, even though the element itself might provide very good acoustic insulation. Even very small gaps can cause a significant increase in the transmission of airborne sound. Problems can also occur where doors, windows, or other openings face onto noisy spaces, such as a circulation space, a busy road, or a school playground. Treatment for reducing of airborne noise. The amount of airborne sound in a space can be reduced by acoustic absorption, which reduces the amount of sound reflecting back into the space from the surfaces enclosing it, by acoustic insulation, which reduces the amount of sound transmitting into the space from an adjacent space through the building fabric, and by the elimination of gaps that might permit direct transmission. Airborne sound transmission can be tested by placing a loudspeaker in a space to generate sound at a range of frequencies, and detecting any resulting sound in an adjacent space with a microphone. The amount of absorption varies greatly depending on the sound frequency, texture, and material. Hard and smooth surfaces tend to have low absorption compared to soft surfaces. These hard surfaces are more likely to cause reflections. The aim of sound reduction is to absorb as much vibration energy as possible. Structure-borne sound transmission. Structure-borne noises are transmitted when sound arises from the actual impact of an object on a building element such as a wall, floor, or ceiling. Examples of this could be footsteps of a person or the sound of an object falling on the floor. Structure-borne sound occurs because the impact causes both sides of the building element to vibrate, generating sound waves. Plumbing noises traveling through pipes are a good example. Another example of structure-borne sound would be tapping on one end of a length of pipe and hearing it at the other end. These vibrations can travel through walls, floors, and ceilings and be heard as noise in adjacent areas. Direct structure-borne sound is generated by the direct application of force to the solid, such as when drilling with a percussion drill. Impact sound is generated by the same principle. This is structure-borne noise generated when walking on a floor or stairs. Indirect structure-borne sound is generated by the transformation of a loud airborne sound source. Parts of the airborne sound cause the body itself to vibrate. For example, a very loud stereo system can cause structure-borne sound vibrations in a wall. The transmission of sound taking place here also have different paths, namely direct transmission, flanking path, transmission via ceiling voids, windows and ventilation ducts, etc. Leakage, flanking path. Flanking or flanking transmission is a term used by acoustical engineers wherein the sound passes around, over the top or under the primary partition separating two spaces. Flanking sound transmission can be especially bothersome in multifamily residential buildings. The best time to guard against flanking transmission is in the design and construction phase of the dwelling. Simply specifying a high-performance wall between adjacent dwelling spaces is no guarantee to sound isolation and privacy upon occupancy. Acoustical Surfaces Incorporated offer both pre-construction and post-construction noise control consultations in addition to all of the products needed to achieve demanded sound isolation. Typical flanking sound transmission pathways can include ceilings, above and through the ceiling space; floors, through floor and floor joist space; through windows; fixtures and outlets, light switches, telephone outlets, and recessed lighting fixtures; shared structural building components, floorboards, floor joists, continuous dry wall partitions, continuous concrete floors, and cement block walls; structural joints, perimeter joints at wall and AMP, floor, through wall, and ceiling junctures; plumbing chases, junctures between the walls and floor slab above or at the exterior wall juncture; around the end of the partition through the adjacent wall. Noise control. A noise problem starts with a noise source which is transmitted through a path and then arrives at the receiver. The noise will be perceived as a problem when the noise is so high as to be a nuisance to the receiver. The severity of the problem depends on the strength of the noise source or the length of the path, that is, how large is the separation between the noise source and the receiver. Sound travels from the source, along a path, to the listener, or receiver. Hence the term SPR, source, path, receiver. Noise control. Control of noise thus involves three considerations. Acoustical treatment at the source of noise. Acoustical treatment of the path it travels, everything between the source and the receiver, and acoustical treatment at the receiver, where the listener is. Controlling noise at source. Most effective to eliminate noise is at the source. Reduce mechanical power. Moving the source to a more distant location or to another area, where its noise will not reach an objectionable level at the listener's place. Adjusting or modifying the source for quieter operation. If for example the source of noise is a mechanism such as a fan or motor, it may be operated at a lower speed. Repairing or servicing the noise source. Mounting the noise source on a resilient base, such as springs or soft pads, to isolate vibration and thus reduce the structure-borne sound arriving at the listener's location. Replacing the noise source with a quieter one. Controlling noise at path. Reflected sound may be reduced by placing sound-absorbing materials on surfaces from which sound will be reflected. The control options are erect barrier, enclose source, isolate vibrations, use active noise control, install absorptive treatment. Controlling noise at receiver. The first and most practical location for successful noise control is at the source. Other practical solutions to noise control are often those involving treatment of the path, which usually involves multiple components: direct, reflected, and flanking. If source control is not practical, another approach would be to treat the problem at the receiver. Sound transmission loss. When sound reaches a barrier, three things can happen: absorption, the sound is absorbed and dissipated as heat; transmission, sound can pass through the barrier; reflection, sound can be reflected back off the barrier. Sound transmission loss, STL, is a quantification of how much sound energy is prevented from traveling through an acoustic treatment. Transmission loss of sound is a measurement of the reduction in sound level of a sound source as it passes through an acoustic barrier. It is the number of decibels that are stopped by the acoustical barrier or the wall and is measured at different frequencies. Sound transmission loss can be defined as a ratio of the sound energy transmitted through a treatment versus the amount of sound energy on the incident side of the material. Sound transmission class. The STC or sound transmission class is a single number method of rating how well wall partitions reduce sound transmission. The STC provides a standardized way to compare products such as doors and windows made by competing manufacturers. A higher number indicates more effective sound insulation than a lower number. STC is highly dependent on the construction of the partition. A partition's STC can be increased by adding mass, increasing or adding airspace, adding absorptive material within the partition. A partition is given an STC rating by measuring its transmission loss over a range of 16 different frequencies between 125–4000 Hz. 125 to 4000 Hz is consistent with the frequency range of speech. The STC rating does not assess the low-frequency sound transfer. Special consideration must be given to spaces where the noise transfer concern is other than speech, such as mechanical equipment or music. Even with a high STC rating, any penetration, air gap, or flanking path can seriously degrade the isolation quality of a wall. Flanking paths are the means for sound to transfer from one space to another other than through the wall. Sound can flank over, under, or around a wall. Sound can also travel through common ductwork, plumbing or corridors. Sound transmission class, STC, is an integer rating of how well a building partition attenuates airborne sound. It is widely used to rate interior partitions, ceilings and floors, doors, windows and exterior wall configurations. In short, STC gives you a rough idea of how much sound a wall, for example, might stop. STC is the most common sound reduction measurement in use. As common as this measurement is, it is quite limited and should not be totally relied upon for real-world soundproofing expectations. Adding mass. The weight or thickness of a partition is the major factor in its ability to block sound. For example, a thick concrete wall will block more sound than a thin gypsum/2x4 wall. Mass is commonly added to existing walls by adding additional layers of gypsum. When the mass of a barrier is doubled, the isolation quality, or STC rating, increases by approximately 5 decibels, which is clearly noticeable. Increasing or adding airspace. An airspace within a partition can also help to increase sound isolation. This, in effect, creates two independent walls. However, the STC will be much less than the sum of the STC for the individual walls. The airspace can be increased or added to an existing partition. A common way to add an airspace is with resilient channels and a layer of gypsum. An airspace of 1.5 inch will improve the STC by approximately 3 decibels. An airspace of 3 inches will improve the STC by approximately 6 decibels. An airspace of 6 inches will improve the STC by approximately 8 decibels. Adding absorptive material in the partition. Sound absorptive material can be installed inside of a partition's airspace to further increase its STC rating. Installing insulation within a wall or floor/ceiling cavity will improve the STC rating by about 4 to 6 decibels, which is clearly noticeable.